In the heart of Copenhagen, on a crisp October day in 1885, a child was born who would one day unravel the deepest mysteries of the universe. His name was Niels Henrik David Bohr. The city around him was steeped in history and intellect, a place where the old world of philosophy brushed against the emerging age of science. The Bohr family home stood near the University of Copenhagen, and it was not just a household. It was an academy of thought. From his earliest years, Niels was surrounded by people who valued the pursuit of knowledge as a noble and almost sacred mission. His father, Christian Bohr, was a respected physiologist, a pioneer in his own right, whose work on the physical chemistry of respiration had already placed him among Denmark's leading scientists. His mother, Ellen Adler Bohr, came from one of Copenhagen's most cultured and intellectual Jewish families. She infused the household with warmth, music, and moral reflection, while Christian filled it with questions about life and the natural world. Together, they created an atmosphere that would shape young Niels's destiny. As a child, Niels was curious, observant, and deeply reflective. He wasn't loud or impulsive. Rather, he watched, thought, and absorbed everything around him with quiet intensity. The Bohr home was often visited by professors, philosophers, and artists. Conversations about science, literature, and ethics flowed as naturally as the evening tea. For Niels, this was education in its purest form, a living dialogue of ideas. The family valued integrity, humility, and intellectual honesty above all. These values would remain deeply rooted in Bohr's scientific philosophy throughout his life. His father's discussions about the human body and the mysteries of life fascinated him. While most children saw science as a subject, Niels began to see it as a language, a way to communicate with nature itself. When Niels entered Gammelholm Latin School, he quickly stood out for his seriousness and his disciplined mind. Unlike many of his classmates who sought quick answers, Niels found joy in lingering over problems. Mathematics and physics captivated him not because they were easy, but because they offered glimpses of something profound, hidden laws that governed everything from falling leaves to starlight. His teachers recognized his unusual combination of patience, imagination, and analytical precision. Yet, his success didn't come from natural ease alone. Niels worked tirelessly. He often stayed up late, absorbed in thought, trying to connect the dots between the abstract formulas he studied and the real world he saw outside his window. His younger brother, Harold Bohr, was equally brilliant, an athlete and mathematician who later became an Olympic soccer player and a renowned mathematician. The brothers shared not only a close bond but also a deep respect for one another's fields. They would debate endlessly about the balance between logic and intuition. These early family conversations sharpened Niels's ability to think critically, to listen deeply, and to appreciate the beauty of both discipline and creativity. It was during these years that the foundation of his scientific character was laid, curiosity tempered by humility, intellect guided by ethics, and a deep desire to understand rather than to conquer nature. In 1903, Niels entered the University of Copenhagen, stepping into a world that would transform his intellectual life. The university at that time was a center of rigorous thought and scientific experimentation. Though Denmark itself was still catching up with the technological revolutions sweeping through Germany and Britain, the young Bohr was drawn immediately to physics, particularly to the teachings of Professor Christian Christiansen, a physicist known for his precision and experimental brilliance. Christiansen's lectures were not easy to follow. They demanded both discipline and imagination. But Bohr found in them a challenge worthy of his ambition. Christiansen noticed the spark in his student, the quiet intensity, the need to question everything, and took him under his wing. At the same time, Bohr's grounding in philosophy began to deepen. He was fascinated by the writings of Søren Kierkegaard, the Danish philosopher whose works explored the paradoxes of existence, truth, and faith. Kierkegaard's belief that truth often lies beyond pure reason resonated with Bohr, even in the realm of science. This interplay between logic and paradox would later become one of the hallmarks of his approach to physics. To Bohr, science was not merely about measuring and predicting. It was about confronting the limits of human understanding. The seeds of this worldview were planted during his university years, nurtured by both scientific rigor and philosophical reflection. Bohr's first major scientific challenge came in 1906, when the Royal Danish Academy of Sciences announced a competition for the best investigation of a practical problem in physics. The topic involved measuring the surface tension of liquids, a complex experimental problem requiring both precision and creativity. Most students would have found it overwhelming, but Bohr approached it with calm determination. He built his own experimental apparatus from scratch, grinding glass, calibrating instruments, and performing countless measurements with extreme care. His father's laboratory provided him the space and tools, but the ingenuity was entirely his own. After months of meticulous work, Bohr presented results so accurate and insightful that the Academy awarded him the gold medal. This achievement was more than an academic triumph. It was a revelation of his character. It showed his ability to combine deep theoretical thinking with patient, hands-on experimentation. The young physicist had demonstrated what would later define his entire career: an unwavering belief that understanding comes not just from equations, but from disciplined interaction with reality. By the time Bohr began his doctoral studies, physics itself was undergoing a revolution. The discoveries of radioactivity, the electron, and the quantum hypothesis were shaking the foundations of classical science. The certainty of Newton's clockwork universe was crumbling. Einstein's theory of relativity had just begun to challenge the very concepts of time and space. Bohr was stepping into this shifting landscape as both a learner and a thinker. His doctoral thesis, completed in 1911, focused on the electron theory of metals. It was an ambitious attempt to connect atomic theory with electrical conductivity, topics that were at the frontier of modern physics. Though the thesis was dense and highly technical, it revealed Bohr's unique way of thinking. He was not satisfied with mathematical descriptions alone. He wanted to understand the physical meaning behind the formulas. Even his early work reflected a search for harmony between theory and observation. During this time, Bohr's relationship with his father deepened further. Christian Bohr's scientific approach, precise, ethical, and rooted in respect for life, profoundly influenced Niels's own scientific integrity. They often discussed not only physiology and physics but also the moral responsibility that comes with discovery. For Niels, science was not a path to fame or power, it was a moral calling, a pursuit of truth that demanded humility before nature's complexity. This perspective would later define his attitude toward both research and teaching. He believed that no scientific idea should ever be treated as absolute, for reality was always richer than human imagination could capture. His respect for uncertainty began long before he formulated it as a principle. It was part of his upbringing. After completing his Ph.D., Bohr's intellectual curiosity led him beyond Denmark. He knew that to engage with the cutting edge of physics, he needed to explore the great scientific centers of Europe. In 1911, he traveled to Cambridge to work with J.J. Thomson, the discoverer of the electron. For Bohr, meeting Thomson was like standing before a living legend. Yet, the collaboration was not as fruitful as he had hoped. Thomson's approach was conservative, rooted in classical ideas, and Bohr found it difficult to express his more unconventional thoughts within that framework. However, the experience was crucial. It taught him the importance of intellectual independence and the courage to question authority, even when that authority was a Nobel laureate. Soon after, Bohr moved to Manchester to work with Ernest Rutherford, whose discovery of the atomic nucleus had just revolutionized atomic science. Rutherford's laboratory was a place of energy and experimentation, filled with bright minds and bold ideas. For Bohr, it was the perfect environment to merge his theoretical insight with real experimental data. Here, he was exposed to the heart of atomic research, studies of radioactivity, alpha particles, and the structure of matter. Rutherford's bold, intuitive approach contrasted sharply with Thomson's caution, and Bohr thrived under it. It was in this atmosphere that his most famous idea, the quantum model of the atom, began to take shape. Yet, the roots of that revolutionary thought went back to his early intellectual influences in Copenhagen's, his father's precision, Kierkegaard's paradoxes, and his own belief that nature reveals itself only to those who listen deeply. By this time, Bohr had developed not only a keen scientific mind, but also a unique philosophical vision. He saw science as a dialogue between mind and matter, not a conquest of one over the other. His early exposure to philosophy had made him aware of the limitations of human perception and language. He realized that even the most precise theories are only approximations, maps, not the territory itself. This humility became one of his defining qualities. It would later help him navigate the turbulent debates about quantum mechanics with grace and patience. He once said that the opposite of a profound truth is often another profound truth, a statement that perfectly captures his philosophical maturity, already evident in his youth. Outside of science, Bohr was deeply human. He loved football, played the piano, and cherished the company of friends. His laughter was quiet but genuine, his manner thoughtful and kind. Students and colleagues later described him as someone who could make the most complex ideas seem simple, not by simplifying them, but by illuminating their essence. This gift of clarity came from his lifelong habit of thinking deeply, of never rushing toward conclusions. He often paused before answering, as if he were weighing the meaning of every word, not out of hesitation, but out of respect for truth. As the 1910s dawned, Europe was on the brink of monumental change. The world was moving toward modernity, and so was physics. The old certainties of classical science were breaking apart, and in their place was emerging a new vision, one in which the observer and the observed were no longer separate, where probability replaced certainty, and where even the smallest particles defied common sense. Bohr stood at the threshold of this transformation, carrying within him a lifetime of influences: his father's scientific discipline, his mother's intellectual warmth, the philosophical echoes of Kierkegaard, and the experimental rigor of Copenhagen's laboratories. These threads would soon weave together into one of the greatest scientific revolutions in human history. The story of Bohr's early life is not just the story of a young man learning physics, it is the story of how a mind is formed, how curiosity, humility, and courage can combine to create a thinker capable of changing the world. His journey from the quiet streets of Copenhagen to the bustling laboratories of England mirrored the evolution of science itself, from certainty to uncertainty, from simplicity to complexity. By the time he began formulating his atomic model in 1913, Bohr had already absorbed the essence of what would define his genius: the ability to see beyond what is measurable, to question what others accepted, and to embrace paradox as a gateway to deeper truth. The winds of Europe in the early 20th century carried both the excitement of discovery and the unease of a world changing faster than anyone could fully understand. For the young Niels Bohr, returning to Copenhagen after his experiences in Cambridge and Manchester, it was as though the universe itself was whispering to him that something deeper awaited exploration. He had seen the atom revealed by Rutherford's experiments and glimpsed the mysteries that classical physics could no longer explain. Yet, before he would give shape to a new vision of the atom, the foundations of his thinking were still quietly maturing, shaped not only by laboratories and equations, but also by human relationships, conversations, and the culture that had nourished him from childhood. Back in Denmark, Bohr accepted a teaching position at the University of Copenhagen. His lectures were unlike those of other professors. He spoke slowly, carefully, weighing each idea as though testing it for balance. Students often said that listening to him was like watching thought take form in real time. He asked questions more than he gave answers, encouraging everyone to think for themselves. What mattered to Bohr was not that his students memorized facts, but that they understood what it meant to think scientifically. to recognize the boundaries of knowledge and the humility required to approach nature's secrets. The same attitude he had absorbed from his father and his early mentors now became his guiding principle as an educator. At home, his family life provided a steady anchor. In 1912 he married Margaretha Ende Rollund, a woman of remarkable grace and intelligence who became both his companion and his intellectual partner. Their marriage was built on trust and deep respect. Margaretha was not a scientist, but she had an extraordinary capacity to listen and to translate complex thoughts into clear language. Throughout Bohr's life, she played a crucial role in helping him articulate his ideas, offering a listener's perspective that kept his explanations grounded. In many of his later letters, he would describe her as his silent collaborator. Their household soon filled with children, 6 sons who would grow up surrounded by books, conversation, and the gentle rhythm of a home dedicated to both family and thought. The years between 1912 and 1913 were a time of intense intellectual ferment. Bohr was re-examining everything he had learned, drawing threads from the work of Planck, Einstein, and Rutherford, yet feeling that none of these theories alone could fully explain atomic behavior. He had already been trained in rigorous experimental methods, yet he sensed that a new form of reasoning was needed. One that combined mathematics, observation, and philosophy into a coherent vision. The questions that occupied him were deceptively simple. How do electrons move around the nucleus? Why do atoms emit light at certain frequencies? But beneath these questions lay something deeper, a search for the unity of nature. Even as his mind turned toward the theoretical problems that would soon make him famous, Bohr continued to draw on the influences that had shaped him as a thinker. His father's emphasis on the physiological harmony of the human body subtly echoed in his approach to physics. Christian Bohr had once said that the beauty of science lies in the interdependence of parts, that no organ could be understood in isolation from the whole. Niels applied this same insight to the atom. He sought to see not just particles and forces, but relationships and balance. Nature, to him, was not mechanical but organic, an intricate web of interactions where understanding required sensitivity, not domination. This sense of unity would later blossom into his principle of complementarity, the idea that seemingly contradictory descriptions can both be true, depending on the context, but even before it was named, the seed of that idea lived within him. Copenhagen, though small compared to the great scientific centers of Europe, was becoming a hub of intellectual vitality, thanks in part to Bohr's growing influence. His home began to serve as an informal salon where young physicists gathered to discuss new discoveries. They debated Planck's quantum hypothesis, Einstein's relativity, and the puzzling results of atomic spectroscopy. The conversations often stretched late into the night, with Bohr listening intently, occasionally pausing to phrase a question that would redirect the entire discussion. Those who were there later recalled that he never dismissed an idea outright. Instead, he would reframe it, turn it around, and look for the truth hidden within. To work with Bohr was to learn that science was not a contest of egos, but a shared journey toward clarity. His love for philosophy remained ever present. He read not only Kierkegaard but also William James, Ernst Mach, and Henry Bergson, thinkers who questioned the relationship between perception and reality. This engagement with philosophy made him unusual among scientists of his generation. He believed that the language of physics was both powerful and limited. Powerful because it allowed precise prediction, limited because it could never capture the wholeness of experience. He often said that physics is not about how nature is, but about what we can say about nature. That distinction would become one of the most profound philosophical contributions of the 20th century, and its roots were planted in these formative years, when Bohr was still trying to reconcile reason with intuition. The intellectual climate of Europe was also influencing him in subtle ways. In Germany, Max Planck and Arnold Sommerfeld were refining the mathematics of quantum theory. In France, Marie Curie's discoveries of radioactive elements were expanding the understanding of atomic transformations. Bohr absorbed all of this knowledge, yet he remained distinctly Danish in spirit, measured, modest, and deeply reflective. While others rushed to publish, he preferred to wait until he had thought through every implication. This patience sometimes frustrated his colleagues, but it was the same patience that allowed him to see connections others missed. He would rather spend days contemplating a single question than produce a hurried answer that might mislead. His time in Rutherford's lab had also given him a new sense of how theory and experiment must complement each other. Rutherford had been a master of intuition, capable of imagining unseen structures from the faintest experimental traces. Bohr admired that skill and internalized it. Yet he also realized that intuition must be disciplined by logic, just as observation must be guided by theory. In this balance he found his scientific rhythm. Every idea, he believed, must pass through 3 stages: wonder, understanding, and communication. First comes the wonder, the spark that awakens curiosity. Then comes understanding, the hard, disciplined effort to make sense of what is observed. Finally, comes communication, the sharing of that understanding in clear, honest language. These 3 stages defined his method and became the invisible structure behind his later breakthroughs. Bohr's personal qualities also played a crucial role in shaping his scientific identity. He was a man of quiet humor, gentle irony, and deep empathy. Colleagues often spoke of his capacity to make everyone feel heard, regardless of their status. When a student made a mistake, Bohr would smile and say, "Yes, but that is a very interesting mistake." To him, errors were not failures, they were steps in the process of discovery. This attitude created an environment of freedom and openness in his classroom and later in his institute. People felt safe to think boldly, to question assumptions, to risk being wrong. That openness was one of his greatest intellectual influences, the belief that truth emerges not from authority, but from dialogue. As the years moved toward World War I, Bohr's world, like that of all Europeans, was shadowed by uncertainty. Yet even in those dark times, his dedication to science did not waver. He saw knowledge as a force for peace, a way to unite nations through shared understanding. When many scientists turned their skills toward warfare, Bohr focused on teaching and developing the next generation of thinkers. This moral stance, inherited from his father's ethical outlook, defined him as more than a physicist. It made him a humanist. He believed that every scientific discovery carried with it a moral responsibility, a theme that would reappear decades later when he confronted the realities of nuclear power. During these years, Bohr also developed a deep appreciation for simplicity in explanation. He often said that the goal of science is not to make things complicated, but to find the simplest possible way of expressing the complex. This search for simplicity was not aesthetic alone, it was a guiding principle that led him to the clarity of his atomic model. Yet simplicity, for Bohr, never meant superficiality. It meant seeing through the complexity to the essential relationships, the core truths that hold everything together. He learned to trust the elegance of an idea as a sign that it was close to nature's own logic. The Copenhagen of Bohr's youth had changed by the end of the 1910s. The world was recovering from war, nations were redefining themselves, and science was entering an age of extraordinary innovation. Amid this transformation, Bohr's reputation grew rapidly. He had already published his model of the atom, a theory that would soon bring him international fame, but those who knew him understood that his achievements were rooted in something far older than a single discovery. They were the fruit of decades of disciplined curiosity, shaped by family, culture, and the intellectual humility of a man who never claimed to possess the final truth. His early life had given him all the ingredients for greatness: curiosity, patience, ethical clarity, and a willingness to live with uncertainty. In the evenings, when the workday ended, Bohr would often walk along the streets of Copenhagen, lost in thought. He was known to be so absorbed that he sometimes forgot to greet friends who passed him by. Yet those walks were not escapes from the world. They were meditations on it. He once remarked that the most important discoveries come when one allows the mind to wander freely, guided not by ambition but by wonder. That quiet wonder had been with him since childhood, since those early days when he watched his father conduct experiments and listened to the murmur of ideas that filled their home. By the early 1920s, the foundations of quantum theory were beginning to solidify, and Bohr was at the center of it. But the depth and calm with which he approached the bewildering new phenomena came directly from his early intellectual training. While others were alarmed by the apparent contradictions of quantum mechanics, Bohr recognized in them the same paradoxical truths that Kierkegaard had written about in philosophy. The idea that two opposing perspectives could both hold meaning. To Bohr, the atom was not a riddle to be solved once and for all, but a symbol of the coexistence of opposites, particle and wave, certainty and uncertainty, knowing and not knowing. This synthesis of science and philosophy was the culmination of his formative years. When one examines Bohr's early life, what becomes clear is that his genius was not the product of sudden inspiration, but of a lifelong cultivation of thought. His intellectual influences were woven into every aspect of his being. From his father, he learned integrity and precision. From his mother, warmth and empathy. From Kierkegaard, the courage to face paradox. From Christensen and Rutherford, the discipline of experiment. And from his own reflections, the understanding that knowledge and humility must always coexist. Each of these threads converged to create the scientist who would later stand before the world and redefine our concept of the atom. In the end, Bohr's early years were not merely a prelude to his discoveries. They were the foundation of his worldview. They taught him that science is not a path of conquest but of dialogue, that truth is never absolute, and that the search for understanding is as much a moral endeavor as it is an intellectual one. When he later said that physics concerns what we can say about nature, not what nature is, he was echoing a lifetime of reflection shaped by family, mentors, and the quiet Danish culture that valued thought over spectacle. Thus, before Niels Bohr changed everything we know about atoms, he had already changed the way one could think about knowledge itself. His early life was a preparation for that transformation. A slow, patient unfolding of mind and spirit in a world poised between old certainties and new mysteries. From the child who listened to his father's scientific debates to the young man walking through Copenhagen with his mind full of questions, Bohr's journey reminds us that revolutions in thought begin long before the discoveries that bear their names. They begin in the silent spaces of reflection, in the conversations that shape our curiosity, and in the courage to ask, again and again, what it truly means to understand. The story of how Niels Bohr revolutionized our understanding of the atom begins not in a moment of sudden inspiration, but in a deep and patient engagement with mystery. The year was 1912. Across Europe, physics was entering a strange new age. The certainties that had once defined the scientific worldview were dissolving. The atom, once thought to be the indivisible building block of matter, had turned out to be a miniature universe filled with invisible forces, subatomic particles, and unpredictable behavior. It was a time of excitement and confusion. For Bohr, the atom represented both a challenge and a promise. The challenge of understanding nature at its most fundamental level, and the promise of uncovering a unity that linked the smallest particles to the largest cosmic laws. Bohr had just returned from his work with Ernest Rutherford in Manchester, and the experience had transformed him. Rutherford's experiments had shown that the atom consisted of a tiny, dense nucleus surrounded by vast empty space. Most of an atom, it turned out, was nothing at all. Yet this discovery raised more questions than it answered. If electrons were orbiting the nucleus like planets around the sun, why didn't they simply fall into it? According to the laws of classical physics, a moving charged particle, like an electron, should constantly lose energy as radiation. Losing energy should make it spiral inward until it collapsed into the nucleus. If that were true, atoms couldn't exist for more than a fraction of a second. But matter clearly did exist. Something was missing, something beyond the reach of classical theory. Bohr could feel that the answer lay somewhere between physics and philosophy. He began to question the very assumptions of classical mechanics. He sensed that the atomic world might obey rules that defied everyday logic. This realization was not easy to accept. It meant that the fundamental principles of motion, energy, and stability might need to be rewritten. Yet Bohr's temperament was suited to this kind of challenge. He was patient, humble before the unknown, and unafraid of paradox. He was ready to listen to nature, even if what it said contradicted human intuition. In early 1913, Bohr began to work intensively on the problem. He had been studying Max Planck's quantum hypothesis, which suggested that energy was not continuous but came in discrete packets, or quanta. Einstein had expanded this idea to explain the photoelectric effect, showing that light itself behaved as if it were made of particles called photons. Bohr took these radical ideas and applied them to the structure of the atom. He proposed that the energy of an electron in an atom could not take on just any value. It could only occupy specific, quantized levels. These energy levels were like steps on a staircase. An electron could stand on one step or another, but never in between. When an electron jumped from one level to another, it would either absorb or emit a precise amount of energy in the form of light. This simple yet revolutionary idea became the cornerstone of his atomic model. The elegance of Bohr's proposal was breathtaking. It explained the spectral lines, the distinct colors of light emitted by atoms when heated or energized, that had puzzled scientists for decades. Each element produced a unique pattern of spectral lines like a fingerprint. For hydrogen, the simplest atom, these lines had been measured with great accuracy, but no classical theory could account for them. Bohr realized that his quantized orbits could. He calculated the allowed energy levels for hydrogen and found that the differences between them matched exactly the observed frequencies of light. It was a moment of pure triumph, the kind of moment that defines scientific history. For the first time, theory and experiment spoke the same language. Yet Bohr's model did more than explain hydrogen's spectrum. It opened a doorway into a new world. It showed that energy, stability, and structure in atoms were governed not by continuous forces but by discrete rules. Nature, it seemed, operated through jumps, abrupt transitions rather than smooth changes. This was a shocking idea. It defied the deeply ingrained belief that nature was continuous, predictable, and deterministic. Even Bohr himself struggled to fully grasp the implications, but the numbers were undeniable and the logic was sound. In May 1913, Bohr published his paper, On the Constitution of Atoms and Molecules, a work that would change science forever. When the paper appeared, the reaction among physicists was electric. Some were thrilled, others skeptical. Rutherford admired Bohr's boldness but doubted whether quantized orbits could be real. Planck himself, whose quantum hypothesis had inspired the model, found it difficult to accept such a departure from classical ideas. Einstein, however, immediately recognized its brilliance. He saw that Bohr had taken the quantum concept beyond light and applied it to matter itself, a daring leap that few would have attempted. Within months, Bohr's atomic model became one of the most discussed topics in physics. It gave a coherent picture of atomic structure at a time when chaos and contradiction reigned. But Bohr's success was not the product of mathematical skill alone, it was the reflection of a deep philosophical insight. He believed that nature reveals itself only when we ask the right kind of questions, and that sometimes, to understand something, we must abandon our familiar way of thinking. He had the rare courage to let go of certainty. The Bohr model was more than a theory, it was a symbol of a new scientific spirit, a willingness to embrace mystery as part of truth. He often said that anyone who is not shocked by quantum theory has not understood it. That sense of astonishment for Bohr was not a flaw but a sign that one was approaching reality. The beauty of the Bohr model lay in its simplicity. It portrayed the atom as a miniature solar system, with electrons revolving around the nucleus in fixed orbits, but with one crucial difference. Those orbits were quantized. Only certain paths were allowed, and electrons could jump between them by emitting or absorbing light of specific wavelengths. The mathematics that emerged from this idea not only explained hydrogen's behavior, but also provided a foundation for understanding more complex atoms. It connected the microscopic world of electrons to the macroscopic world of light and color, bridging two realms that had once seemed unrelated. Still, Bohr knew that his model was an approximation. He understood that it could not account for all the complexities of atoms heavier than hydrogen. But he also knew that scientific progress comes in steps. Each theory is a stage on the journey toward a deeper truth. His humility allowed him to see his own model not as an end, but as a beginning, a stepping stone toward a more complete quantum theory. This humility made him different from many of his contemporaries. He never claimed finality, only progress. For him, the purpose of science was not to achieve certainty but to refine understanding. The impact of Bohr's model rippled far beyond physics. It reshaped chemistry by explaining why atoms form bonds, why elements have distinct chemical properties, and why the periodic table has its characteristic pattern. It laid the groundwork for the development of quantum mechanics, which would later revolutionize technology and philosophy alike. In classrooms and laboratories across the world, students began to picture the atom as Bohr had described it, a nucleus with electrons circling in elegant orbits. The image became so iconic that it entered popular culture, appearing in textbooks, logos, and artworks as the universal symbol of science itself. Though later refinements would replace Bohr's model with more sophisticated quantum theories, its conceptual power remains unmatched. In 1922, less than a decade after his model's publication, Bohr was awarded the Nobel Prize in Physics for his services in the investigation of the structure of atoms and of the radiation emanating from them. The award was not just for a single discovery, but for the birth of a new way of seeing the world. When Bohr accepted the prize, he spoke not of personal triumph, but of the collective human quest for understanding. He reminded his audience that every discovery stands on the shoulders of others, that science is a continuous dialogue between generations. This humility and sense of interconnectedness had been with him since his youth, and they defined his entire career. Even after the Nobel Prize, Bohr continued to refine his ideas. He collaborated with some of the brightest minds of the age, Heisenberg, Pauli, Born, and Schrödinger, each of whom brought new insights to the growing field of quantum mechanics. Yet, despite the rise of new mathematical formalisms that went beyond his 1913 model, Bohr's conceptual framework remained central. His idea of quantized energy levels became the skeleton upon which the entire quantum theory of atoms was built. The language of quantum numbers, orbital transitions, and discrete energy states all trace their origin to his revolutionary insight. What made Bohr's model so powerful was not only that it worked mathematically, but that it offered a way to visualize the invisible. Before Bohr, the atom was a mystery clouded in abstraction. After Bohr, it became imaginable. He had given humanity a mental picture of the microscopic world, a way to see beyond the limits of perception. That image, however simplified, bridged the gap between the known and the unknown. It made the idea of quantum physics accessible, even poetic. Scientists could now speak of electrons leaping from one orbit to another, releasing light as they did so, a dance of energy that mirrored the rhythms of the universe itself. But behind the elegance of the theory lay a deeper philosophical question that haunted Bohr. What does it mean to know something about nature? His model worked, yet it described something no one could actually see. The orbits, the transitions, the quantized energy levels. These were not visible realities but conceptual tools. They were ways of describing the behavior of matter, not pictures of what truly existed. Bohr began to sense that in physics, the act of measurement and the act of description were inseparable. This realization would later lead him toward his most famous philosophical contribution, the principle of complementarity. But even in 1913, That seed of thought was already growing within him. The success of Bohr's model also came at a time when the world outside science was changing rapidly. Europe was sliding toward war, and the optimism of the pre-war era was fading. Yet Bohr's discovery stood as a beacon of intellectual hope, a reminder that even amid chaos, the human mind could reach toward harmony. His model was not only a scientific breakthrough, but a cultural one. It represented the triumph of reason over confusion, of clarity over chaos. It showed that by asking questions with honesty and imagination, humanity could uncover order hidden within apparent randomness. For Bohr himself, the discovery was both exhilarating and humbling. He once said that the purpose of science is to reduce mystery without eliminating it, to bring us closer to understanding without pretending we can grasp everything. The atomic model did exactly that. It reduced some mysteries but revealed deeper ones. It showed that the universe operates on rules that are elegant but strange, precise but unpredictable. For Bohr, this strangeness was not a defect in human knowledge, it was a reflection of nature's richness. The more we learn, he believed, the more we should be amazed. In the years following his atomic breakthrough, Bohr often revisited his early calculations, refining them, testing their limits, and teaching new generations of physicists to think with both rigor and wonder. The world was moving toward a new era of science, an era that would soon produce the quantum mechanics of Schrödinger and Heisenberg, the uncertainty principle, and the strange duality of particles and waves. Bohr's model was the first step on that journey. Without it, the road to quantum mechanics might have been much longer and far less clear. As he looked back on his 1913 paper later in life, Bohr recognized its limitations but never regretted its simplicity. He knew that every great theory begins as an approximation. What mattered to him was not perfection but insight, the ability to capture something true, even if only partially. He once remarked that accuracy and truth are not always the same. A theory can be true in spirit, even if incomplete in detail. His atomic model was precisely that, a truthful vision of how energy, matter, and light interact, even if the full picture lay beyond its reach. After 1913, Niels Bohr's atomic vision began to ripple outward, transforming the landscape of modern science. What had started as a single theoretical paper soon became the foundation for an entirely new worldview. Across Europe, laboratories echoed with excitement as physicists tried to test, refine, and challenge his ideas. Young researchers flocked to Copenhagen, drawn by the quiet intensity of Bohr's mind. They found not a lecturer commanding from a podium, but a listener, someone who drew insight out of others through patient dialogue. The institute Bohr would later establish became a place where ideas were not merely taught, but lived, debated, and reimagined every day. In these early years, the Bohr model continued to prove its strength. It accurately predicted the spectra of other simple atoms and ions, confirming that quantized orbits were not a strange coincidence, but a fundamental law of nature. Yet Bohr was never satisfied with success alone. He knew that every discovery opened the door to deeper questions. As he explored the fine details of atomic behavior, he encountered new puzzles that the original model could not explain. The orbits were elegant, but real atoms exhibited subtle variations that hinted at forces and interactions more complex than the model allowed. Bohr realized that the next stage of progress would require not just new equations but a new philosophy of measurement itself. By the mid-1920s, physics was standing on the edge of another revolution. Werner Heisenberg, a brilliant young German physicist who had studied under Bohr, introduced matrix mechanics, a mathematical formulation that described atomic phenomena without referring to orbits at all. Soon after, Erwin Schrödinger developed wave mechanics, presenting the atom not as a miniature solar system, but as a cloud of probabilities. Both approaches seemed to contradict Bohr's earlier picture, yet both owed their existence to the conceptual foundation he had built. When Heisenberg brought his new theory to Copenhagen, he was anxious about how Bohr would respond. But Bohr welcomed him with warmth and curiosity. Over long nights of discussion, sometimes stretching until dawn, the two wrestled with the meaning of the equations. Their debates were intense, but full of mutual respect. Bohr's philosophical patience balanced Heisenberg's youthful boldness, and out of their dialogue emerged one of the most profound ideas in the history of science: the principle of complementarity. Complementarity proposed that nature could exhibit seemingly contradictory behaviors that were both true, depending on how one looked. Light, for example, could behave as both a particle and a wave, but never both at once. The same was true for electrons. The act of measurement determined which aspect of reality would appear. This was not merely a technical statement about experiments, it was a deep commentary on the limits of human knowledge. Bohr argued that the properties of quantum objects could not be separated from the conditions under which they were observed. In other words, the observer and the observed were intertwined in an inseparable dance. The universe was not a stage upon which events unfolded independently of us. It was an active dialogue between mind and matter. Many scientists found this idea unsettling. Einstein, in particular, could not accept it. For him, physics was about objective truth, about discovering how the world really is, regardless of who observes it. He famously challenged Bohr, saying, "God does not play dice with the universe." Bohr's reply was calm but firm. Einstein, "Stop telling God what to do." Their debates became legendary, a clash of two giants whose friendship survived their disagreements. To Bohr, uncertainty was not a flaw in nature but a sign of its depth. He believed that the quantum world revealed a fundamental truth, that knowledge is always partial, that reality is richer than any single description can capture. The principle of complementarity became not just a scientific idea, but a philosophy of life, an acceptance that truth often comes in pairs of opposites, and that understanding requires humility. As these debates unfolded, Bohr's influence spread far beyond his own research. His Copenhagen Institute became the spiritual home of quantum mechanics. Young physicists from around the world, Pauli, Dirac, Fermi, and others, came to study under his guidance. The atmosphere there was unlike any other scientific center. There were few formal lectures and no rigid hierarchy. Instead, discussions flowed freely, driven by curiosity and mutual respect. Bohr would often pause mid-conversation, his face thoughtful, his hands gesturing as if shaping an invisible concept. He encouraged others to speak, to question, to think aloud. He had an extraordinary ability to see the value in every idea, even those that seemed vague or contradictory. For him, confusion was not failure, it was the beginning of clarity. Many of his students later said that talking with Bohr felt like being drawn into the very heart of nature's mystery. In the 1930s, Bohr's attention turned to the atomic nucleus itself. He proposed the liquid drop model, imagining the nucleus as a droplet of incompressible fluid whose surface tension could explain the way it deforms and divides. This model would later prove crucial in understanding nuclear fission. When scientists in Germany discovered in 1938 that uranium atoms could split, releasing enormous energy, Bohr immediately grasped the significance. He realized that this process could unleash power on a scale never before imagined. At the same time, he feared its potential for destruction. As World War II erupted, Bohr's life was thrown into turmoil. Being of partial Jewish descent and an outspoken advocate of intellectual freedom, he became a target of Nazi occupation. In 1943, he was forced to flee Denmark in a dramatic escape, smuggled across the sea to Sweden, then flown to England in the cramped hold of a small military aircraft. From there, he eventually reached the United States, where scientists were working on the secret Manhattan Project. Bohr's role in the project was unique. He was not an engineer or a military strategist. He was a philosopher, scientist who reminded others of the moral dimensions of their work. He met with figures such as Oppenheimer and Fermi, offering insight into the physics of fission. But he also urged caution and international cooperation. He envisioned a world where nuclear energy would serve peace rather than war. After witnessing the destructive power of the atomic bomb, Bohr became a passionate advocate for openness in science. He believed that secrecy and competition would only breed fear, while shared knowledge could foster trust among nations. His appeals to world leaders were not always heeded, but his voice carried a moral authority that few could ignore. In the post-war years, Bohr returned to Copenhagen and resumed his work at the institute that now bore his name. Though weary from the experiences of war, he remained intellectually vibrant. Younger generations continued to seek his wisdom, and his home became a meeting place for thinkers from across disciplines: physicists, philosophers, even poets. Bohr's conversations often drifted beyond science into questions of meaning, ethics, and human unity. He spoke of the need for complementarity not only in physics but in society, the balance between freedom and responsibility, between individual and collective good. His mind moved effortlessly between equations and ethics, seeing both as expressions of the same search for harmony. Even as new developments in quantum field theory and particle physics began to overshadow his early models, Bohr's influence endured. The conceptual framework he had built remained the foundation of modern physics. Every student who learned about energy levels, emission spectra, and quantum transitions was walking in his footsteps. More importantly, his philosophical approach, his insistence on clarity, humility, and openness, became a model for scientific inquiry itself. To think like Bohr was to recognize that truth is never final, that every answer gives rise to deeper questions. He taught that uncertainty is not something to be feared, but something to be understood, embraced, and used as a guide. By the 1950s, the atomic age had transformed the world. Nuclear energy powered cities, and quantum mechanics had given birth to new technologies: transistors, lasers, and the first steps toward computers. Each of these advancements could trace its lineage back to Bohr's early insight that energy is quantized and that matter behaves in discrete steps rather than continuous flows. It is astonishing to think that the simple idea of electrons jumping between energy levels had blossomed into an entire civilization's technological foundation. Bohr lived long enough to see this transformation, and though he remained modest, one could sense quiet pride in his eyes when he saw how far humanity had come. Yet he also warned of imbalance. In a world racing toward material progress, Bohr reminded people that wisdom must keep pace with power. He saw science as a double-edged sword, capable of creation and destruction alike. His dream was not merely to understand atoms, but to help humanity understand itself. In his later writings, he often reflected on the parallels between physics and human behavior. Just as quantum objects can display dual natures, so too can societies hold opposing truths that must coexist: competition and cooperation, freedom and restraint, faith and reason. For Bohr, complementarity was not just a principle of physics but a philosophy of coexistence. In 1962, as he grew older, Bohr began to compile his reflections into essays that blended scientific insight with humanistic vision. He revisited his earliest days of discovery, recalling the excitement of 1913 and the wonder he felt upon realizing that nature's order could be so strange yet so precise. He wrote that every step in science should deepen our sense of awe, not diminish it. Knowledge, he said, should make us more humble, not more proud. When asked how he had found the courage to challenge classical physics, Bohr replied that it was not courage but necessity. Nature had left no other choice. The facts demanded a new way of thinking, and he simply followed where they led. Bohr's final years were peaceful but reflective. He continued to receive visitors, to mentor, and to speak softly about the unity of knowledge. Those who met him described his presence as calming, almost luminous. He had an aura of quiet certainty that came not from arrogance but from deep understanding. When he passed away in 1962, the scientific community mourned not only a great physicist, but a moral philosopher of the modern age. His funeral in Copenhagen was attended by leaders of science from around the world, each aware that they were saying goodbye to a man who had reshaped human thought. In the decades since his death, Bohr's legacy has only grown. His name adorns research institutes, his face appears on currency, and his ideas continue to influence fields far beyond physics. from biology to psychology to philosophy. The very notion of complementarity has found echoes in modern discussions of consciousness, complexity, and systems theory. His atomic model, though superseded in detail, remains a symbol of the moment humanity first peered into the heart of matter and found a universe of order hidden within chaos. Looking back, it is clear that Bohr's true achievement was not merely solving the riddle of the atom, but teaching us how to think differently about reality itself. He showed that knowledge and mystery are not enemies but partners. Every time science unveils a new truth, it also reveals the vastness of what remains unknown. Bohr embraced that paradox with grace. He often said that the task of science is not to remove mystery, but to live more deeply within it. His atomic model may have begun as a mathematical theory, but it ended as a meditation on existence, a reminder that the universe, in all its strangeness, is comprehensible enough to inspire wonder and mysterious enough to keep us searching. As the 20th century gave way to the 21st, the principles that Bohr helped establish became the bedrock of modern technology. Quantum mechanics now governs the chips inside computers, the sensors in satellites, and the algorithms behind communication networks. When we speak through digital devices or explore the depths of space, we are unknowingly touching the legacy of a man who once sat in a quiet room in Copenhagen, pondering why electrons do not fall into their nuclei. His questions had reshaped the world. Even today, physicists continue to debate the meaning of Bohr's ideas. Was complementarity merely a philosophical interpretation, or does it point to something fundamental about reality itself? The very persistence of these questions is part of his gift. Bohr's work refuses to settle into finality. It keeps the conversation alive, reminding every new generation that understanding is a journey, not a destination. The atom, once imagined as solid and indivisible, has become a symbol of uncertainty and potential. That transformation began with Bohr's willingness to think the impossible. When one reflects on the arc of his life, from the quiet streets of Copenhagen to the halls of international science, it becomes clear that Niels Bohr was more than a scientist. He was a bridge between eras, the last of the classical thinkers and the first of the quantum philosophers. His atomic model stands as both a scientific milestone and a work of art, precise, beautiful, and deeply human. It invites us to see the world not as a collection of parts, but as an interconnected whole, where every particle, every light wave, and every human thought participates in the unfolding story of the universe. Bohr's revolution was not only in equations, it was in perception. He taught humanity that the smallest things can contain the greatest mysteries, and that to understand the atom is, in a sense, to understand ourselves. The universe, he showed, is not made of certainty but of possibilities, a vast web of relationships waiting to be explored. His legacy endures in every experiment, every question, and every moment of wonder when a human mind dares to ask, why? And perhaps that is the final truth of Bohr's atomic vision, that the quest to understand matter is also the quest to understand meaning. In the shimmering boundaries between light and darkness, between knowledge and mystery, between what is known and what is felt, lies the spirit of discovery that Niels Bohr gave to the world. His model may have begun with a single atom of hydrogen, but its echo continues through every corner of modern thought, a quiet, eternal reminder that reality is both knowable and endlessly profound. The year was 1913. Europe stood at the edge of modernity, its cities alive with invention, its laboratories glowing with the promise of discovery. In that year, a 30-year-old physicist named Niels Bohr published a paper that would change the course of human thought. The paper was modest in size, but its implications were infinite. In a few clear pages, Bohr introduced an idea so radical that it shattered centuries of scientific certainty. The idea that the atom, once believed to be a miniature solar system governed by classical mechanics, followed an entirely different set of laws, unseen and almost mystical in nature. Before Bohr, the atom was a puzzle no one could solve. The model proposed by Ernest Rutherford, a tiny, dense nucleus orbited by electrons, was elegant but incomplete. According to the laws of electromagnetism, those orbiting electrons should continuously radiate energy, spiral inward, and collapse into the nucleus within a fraction of a second. Matter itself, by that logic, should not exist. The universe should have dissolved the moment it began. Yet it persisted, stable and luminous. Something deeper was at work, something that defied the logic of Newton's world. And it was Bohr who dared to ask the unthinkable. What if the laws that governed the visible world no longer applied within the atom's hidden depths? Bohr proposed that electrons did not move in continuous paths, but occupied discrete orbits, or energy levels. They could jump between these levels, absorbing or emitting light in the process, but they could never exist in between. This was a profound departure from classical reasoning. It meant that energy, and therefore nature itself, was not smooth but quantized, structured like a staircase rather than a ramp. With that simple but revolutionary concept, Bohr merged Rutherford's nuclear atom with Max Planck's quantum theory, creating a hybrid that would form the foundation of all future atomic science. At first, the scientific world was puzzled. Many physicists regarded Bohr's model as a bold mathematical trick, useful perhaps for explaining hydrogen spectra, but hardly a reflection of reality. Others dismissed it as too abstract, too speculative. Yet, quietly, evidence began to mount in his favor. The sharp spectral lines of hydrogen, long a mystery to physicists, matched perfectly with Bohr's calculated energy transitions. Suddenly, the strange and beautiful colors emitted by gases under electric excitation made sense. Light was not a continuous wave, but a fingerprint of atomic identity. Every element possessed its own unique pattern, its own quantum rhythm. For the first time, scientists glimpsed the architecture of the invisible. Bohr's atom was not just a theory, it was a revelation. It showed that the universe operated by laws far subtler than anyone had imagined, laws that were probabilistic, not deterministic, layered, not linear. In a world accustomed to certainty, Bohr introduced uncertainty as a fundamental principle of existence. And though he himself would later refine and even challenge aspects of his model, the 1913 atom marked the dawn of quantum mechanics, the science of the very small that would go on to shape the very large. Across the laboratories of Europe, the echoes of Bohr's discovery spread like wildfire. At first in Manchester, where Rutherford's students debated its implications late into the night, then in Berlin, where young geniuses such as Sommerfeld and Einstein pondered its consequences for physics and philosophy alike. For many, it was both thrilling and terrifying. If Bohr was right, then the world was not a tidy machine, but a dynamic tapestry woven of probabilities and potentialities. Atoms no longer followed predictable paths, they existed in states of possibility until observed. Reality itself had become participatory, fluid, relational, and mysterious. This new atomic vision was not just scientific, it was spiritual in its depth. For Bohr, understanding the atom meant rethinking the very act of observation. He believed that what we see is shaped by how we look. This insight would mature over the following decade into his famous principle of complementarity. The idea that contradictory descriptions of nature can both be true, depending on the conditions of measurement. But even in 1913, its seeds were already there. Bohr's atom forced humanity to confront the limits of knowledge and to accept that truth could wear many faces. In those early years, Bohr's model became a bridge between the seen and the unseen. It explained not only the colors of light, but the stability of matter itself. Why didn't atoms collapse? Why did elements behave predictably in chemical reactions? Bohr's quantized orbits provided the answer. Each atom was a tiny universe balanced delicately by the rules of quantum jumps. The stability of the cosmos, from the light of stars to the chemistry of life, depended on these invisible leaps. Every atom in every human body was performing its silent dance according to the rhythm Bohr had uncovered. Yet Bohr's own mind was never at rest. He was deeply aware that his model was only an approximation, a step toward a greater truth. As experimental precision improved, discrepancies began to appear. The fine details of hydrogen spectrum could not be fully explained by circular orbits alone. Bohr welcomed these inconsistencies, for to him they were signs of progress. Every great and deep difficulty, he once said, bears in itself its own solution. His humility was not weakness, it was strength. He never clung to an idea as a possession. He saw theories as temporary bridges between mystery and understanding, bridges that must eventually be rebuilt when deeper waters are reached. In the years following his model's publication, Bohr refined his ideas through tireless collaboration. He traveled between Cambridge, Göttingen, and Munich, engaging with some of the most brilliant minds of the era. These were the crucibles of the new physics, places where theory and experiment met in feverish creativity. Heisenberg, Pauli, and Sommerfeld were among the rising stars inspired by his thinking. The discussions were often intense, even philosophical, stretching into long nights of argument and wonder. But through them all, Bohr remained the quiet center, patient, deliberate, always seeking harmony in contradiction. He was not a man of grand gestures or scientific theatrics. Those who worked with him described an atmosphere of calm intensity. When faced with a problem, Bohr would sit in long silence, eyes distant, as if listening to the universe itself. Then he would speak, softly, hesitantly, but with words that carried the weight of deep thought. He once told a student, "Never express yourself more clearly than you can think." This humility of expression reflected the humility of his science. He understood that nature's truth could not be forced into human language. It could only be approached with care and respect. Bohr's atomic model also had a profound cultural resonance. It arrived at a time when the world itself was fragmenting, politically, artistically, philosophically. The Great War had shattered faith in classical order, and modernism was rising in art and literature. Bohr's vision of the atom, discrete, discontinuous, yet harmonious, mirrored this new reality. Painters like Kandinsky and poets like Eliot were experimenting with fragmentation and abstraction, just as physicists were discovering discontinuity in nature. The old ideals of continuity and certainty were dissolving in every field of human endeavor. Bohr's atom was both a scientific and symbolic reflection of this transformation, a world no longer bound by straight lines, but by leaps of meaning. Even Einstein, though skeptical of Bohr's later interpretations, admired the beauty of his early model. He called it an act of genius, recognizing that it captured something essential about nature's order. For Einstein, it was the beginning of a profound philosophical conversation that would span decades. The two men, so different in temperament, became intellectual foils, one seeking deterministic clarity, the other embracing paradox. Their debates would shape not only the science of the 20th century, but the very language of human understanding. As the 1920s unfolded, Bohr's model became both the foundation and the springboard for new developments. Schrödinger's wave mechanics and Heisenberg's matrix mechanics emerged as deeper, more comprehensive descriptions of atomic behavior, yet both owed their lineage to Bohr's conceptual leap. Heisenberg once said that without Bohr, there would have been no quantum mechanics, only fragments of insight scattered across Europe. Bohr had provided the vision that connected them. His 1913 model was the seed from which the forest of modern physics would grow. But Bohr's genius lay not merely in his discoveries, but in his way of thinking, a rare synthesis of imagination and discipline, of philosophy and precision. He saw equations not as ends in themselves, but as languages attempting to speak the unspeakable. To him, the atom was not a thing but a relationship, a pattern of interactions, a network of possibilities. This way of seeing would later influence not only quantum physics, but the entire worldview of the modern age. It was a way of thinking that resonated with Eastern philosophies, which Bohr deeply admired. He was particularly drawn to the yin-yang symbol, which he adopted for his family coat of arms after receiving the Order of the Elephant, Denmark's highest honor. Beneath it, he inscribed a Latin phrase, contraria sunt complementa, or opposites are complementary. It was both his personal creed and his scientific philosophy. Through Bohr's work, humanity's perception of reality was forever altered. The atom, once thought to be the smallest indivisible particle, became a realm of mystery and motion. Certainty gave way to probability, and the mechanical universe of Newton transformed into the quantum universe of Bohr. Unpredictable yet deeply ordered, chaotic yet lawful. The shift was not only scientific but existential. It challenged the human need for absolute answers and replaced it with a vision of interconnectedness and humility. Every scientific revolution changes not just what we know, but how we know. Bohr's revolution did both. He gave humanity the tools to probe the subatomic world and the wisdom to accept its paradoxes. His model of the atom, though simple by modern standards, remains one of the most beautiful expressions of scientific insight ever created. It marked the moment when physics became not just the study of matter, but the study of meaning, when scientists stopped asking merely what nature does and began to ask why. As the years went on, the Bohr atom found its way into classrooms, laboratories, and imaginations across the globe. It became the universal symbol of science itself, the tiny solar system of electrons circling a nucleus, glowing with energy and possibility. Even though later models replaced its details, its essence endured. For millions of people, it represented the gateway to understanding, the point where mystery met reason, where curiosity became knowledge. And behind that enduring image stood the quiet figure of Niels Bohr, whose humility and depth of thought turned the invisible into the imaginable. Bohr once said that when it comes to atoms, language can be used only as poetry. And indeed, his own life and work read like a poem, a meditation on the harmony of opposites, the balance of light and darkness, certainty and doubt. His model of the atom was more than a scientific construct, it was a reflection of his soul, an attempt to capture, in mathematical form, the delicate dance of existence itself. In Copenhagen, Bohr's laboratory became a magnet for the brightest minds of his time. Young physicists such as Werner Heisenberg, Wolfgang Pauli, and later Max Born found in Bohr not just a teacher but a philosophical guide. He had an unusual approach to science. He did not seek quick answers but rather clarity of understanding. Bohr's discussions were famously deep and reflective. He believed that every concept in physics must be examined not only for what it explained, but also for what it meant. It was this combination of intellectual rigor and philosophical curiosity that turned the Bohr Institute into the birthplace of modern quantum mechanics. The idea of quantum leaps, electrons jumping from one orbit to another, was initially met with resistance because it contradicted everything scientists knew about motion. In the macroscopic world, things moved smoothly, nothing jumped discontinuously from one state to another. Yet Bohr's model demanded that the subatomic world obey a new logic. When electrons shifted between orbits, they did so instantaneously, without existing in between. This concept defied visualization, but its mathematical accuracy could not be denied. For Bohr, the purpose of physics was not to describe what could be imagined, but to express what could be measured and predicted. Heisenberg, deeply inspired by Bohr's thinking, began to formalize this new understanding into what would become matrix mechanics, the first formulation of quantum mechanics. Meanwhile, Schrödinger developed wave mechanics, using continuous mathematical waves to describe particles. Both theories seemed contradictory, one discrete, one continuous, but Bohr insisted that both were necessary perspectives. This idea evolved into what Bohr later called the principle of complementarity, suggesting that reality could be described in different, equally valid ways depending on how it was observed. An electron could behave like a wave or a particle, but never both at once. It was not a flaw in physics, but a reflection of nature's duality. Bohr's deep trust in experimental evidence anchored his theories in reality. The emission spectra of hydrogen, those precise lines of color seen when light from excited hydrogen atoms passed through a prism, provided undeniable proof that electrons occupied specific energy levels. Each jump from a higher to a lower level released energy in the form of light, with a frequency corresponding exactly to Bohr's predictions. The match between theory and experiment was so perfect that it silenced most skeptics. This success became a cornerstone of quantum theory, linking abstract mathematics with observable phenomena. As the years passed, Bohr's vision of the atom grew more sophisticated. He realized that his early model, while revolutionary, was still incomplete. The discovery of new elements and the complexity of multi-electron atoms revealed limitations in his framework. But instead of being discouraged, Bohr saw this as an invitation to explore further. He proposed the concept of electron shells and subshells, explaining why certain elements shared chemical properties and why the periodic table had its unique structure. His insights bridged physics and chemistry, showing that the mysterious world of quantum mechanics shaped the very matter that built our universe. Bohr was also a man of immense humility. He often described his theories as tentative, always subject to refinement. His favorite saying was, "Every great and deep difficulty bears in itself its own solution." He believed that paradoxes were not problems to be eliminated, but signposts pointing toward deeper truths. This philosophical openness made him not just a scientist, but a thinker who shaped how generations of physicists approached the mysteries of existence. By the mid-1920s, Bohr's influence had reached far beyond the walls of his institute. He traveled widely, lecturing across Europe and the United States, spreading the quantum revolution. His soft-spoken manner, reflective pauses, and poetic way of expressing complex ideas earned him immense respect. He was not a man of ego but of ideas, always emphasizing collaboration over competition. Under his mentorship, a new generation of scientists began to see the atom not as a miniature solar system, but as a dynamic, probabilistic field of possibilities. The idea of quantum leaps began to shape technologies that would later define the modern world. The principles underlying Bohr's atomic theory became essential for the development of semiconductors, lasers, and nuclear energy. Each discovery traced its lineage back to the quantum transitions he had first described. Though Bohr could never have imagined computers or smartphones, the equations that emerged from his work became the invisible foundation of the digital age. Bohr's way of thinking also redefined the relationship between observation and reality. He taught that the act of measurement was not passive, it changed what was being measured. This radical idea meant that at the quantum level, there was no objective reality independent of observation. The observer and the observed were intertwined. It was a profound shift in human understanding, one that echoed beyond physics into philosophy, psychology, and even art. Bohr had shown that certainty was an illusion, and that the universe at its core was a dance of probabilities. As quantum mechanics matured, Bohr continued to refine his interpretation. His debates with Einstein, which would become legendary, centered around these very ideas. Einstein famously objected, saying, "God does not play dice," rejecting the randomness inherent in Bohr's universe. Bohr, in his calm and deliberate way, replied, "Einstein, stop telling God what to do." This exchange captured the essence of their intellectual struggle, the battle between determinism and uncertainty, between the classical and the quantum. Bohr's perspective prevailed, not through persuasion but through the overwhelming success of quantum mechanics in predicting experimental results. Behind his scientific brilliance, Bohr remained deeply human. He was known for his kindness, his patience, and his belief in the moral responsibility of scientists. He encouraged open dialogue and welcomed disagreement, seeing it as a pathway to truth. His institute in Copenhagen was not just a place of research, but a sanctuary for free thought during turbulent times in Europe. Many scientists fleeing political oppression found refuge under Bohr's roof, drawn by his integrity and compassion as much as by his intellect. The legacy of Bohr's quantum leaps was not just a new theory of atoms, but a new way of seeing the universe, a way that embraced uncertainty, complexity, and paradox. He showed that even in the smallest particles lay the fingerprints of profound truth, and that by studying them, humanity could glimpse the architecture of creation itself. His ideas continue to resonate in the work of modern physicists who probe deeper into quantum fields and subatomic structures, still guided by Bohr's light. In the grand narrative of science, Bohr's contribution marks a moment when knowledge took a leap of its own. A quantum leap, transcending the boundaries of imagination. His courage to defy convention, his openness to mystery, and his unshakable belief in the unity of thought and nature transformed physics into a reflection of human curiosity itself. The atom, once a symbol of solidity, became under Bohr's vision a realm of infinite wonder, a universe within a universe, where energy, motion, and existence dance to the rhythm of unseen laws. And so, as his story continues to inspire generations, the truth becomes clear. Niels Bohr didn't merely explain atoms. He taught humanity to think differently about reality. He showed that knowledge is not the absence of mystery, but its evolution, that every answer opens a new question, and that in the smallest scales of the universe, we may find not chaos, but harmony disguised as uncertainty. Through Bohr, the quantum world became not just a field of study, but a mirror reflecting the boundless depth of human understanding. In the world of physics, few intellectual exchanges have reached the depth and drama of the debates between Niels Bohr and Albert Einstein. Their discussions were not arguments between rivals, but rather dialogues between two giants who sought to uncover the most profound truths about the universe. Both men were visionaries, yet they stood on opposite sides of one of science's greatest philosophical divides. Einstein, the architect of relativity, believed the universe was governed by precise laws, elegant and deterministic. Bohr, the father of the quantum atom, saw a universe ruled by probabilities, where uncertainty was not a flaw, but a fundamental feature of nature itself. Their debates were not confined to laboratories or equations. They were a philosophical battle about the meaning of reality. It began in the 1920s, a time when quantum mechanics was emerging as a strange but powerful new theory. The classical world of Newton and Maxwell had been clear and predictable. If one knew all forces and positions, one could, in theory, predict the future. But Bohr's quantum world did not play by those rules. It suggested that particles behaved like waves, that observation changed outcomes, and that some events could only be described statistically. Einstein could not accept this. For him, randomness was a sign of incomplete understanding. He famously said, "God does not play dice with the universe." Bohr, however, countered with quiet conviction, "Einstein, stop telling God what to do." Their exchanges became legendary during the Solvay conferences, gatherings of the greatest minds of physics in the early 20th century. In those grand halls, filled with chalkboards and the tension of discovery, Einstein would challenge the foundations of quantum theory with thought experiments designed to expose its contradictions. Bohr, calm and deliberate, would respond with careful reasoning, defending the quantum view that the act of observation is inseparable from what is being observed. To Einstein, this seemed unacceptable. Reality, he argued, must exist independently of human measurement. Bohr, however, believed that physics was not about describing an independent reality, but about what could be known and measured. These debates were more than scientific arguments. They were reflections of two ways of seeing the universe. Einstein's view was that nature was a grand, ordered mechanism where every event had a cause, even if it was hidden from us. Bohr's vision was more poetic and paradoxical, that reality itself was fluid, unfolding only in interaction with consciousness. In Bohr's interpretation, there was no single picture of truth. The universe could be both wave and particle, depending on how it was examined. To him, this duality was not confusion, it was completeness. The clash between these two ideas shaped the philosophical foundation of modern physics. Each challenge from Einstein forced Bohr and his colleagues to strengthen the theory of quantum mechanics. One of the most famous challenges came in the form of the Einstein-Podolsky-Rosen paradox, which questioned whether quantum mechanics was a complete theory. Einstein argued that if quantum mechanics were true, then two particles could remain connected over vast distances, influencing one another instantaneously, a concept he mockingly called spooky action at a distance. Bohr responded that this was not a flaw, but a revelation. Nature itself was deeply interconnected, and measurement on one side could affect the description of the other, even across space. Years later, experiments confirmed that Bohr was right. Quantum entanglement, as it came to be known, became one of the most mysterious and essential features of the subatomic world. What Einstein once considered impossible became the basis for modern technologies like quantum computing and secure communication. In this sense, Bohr's philosophical courage to accept uncertainty and connection as natural proved to be one of the most visionary steps in science. Their debates continued for years, always marked by mutual respect. Though they disagreed deeply, Bohr admired Einstein's brilliance and moral strength, while Einstein respected Bohr's intellect and humility. Together, they embodied the essence of scientific progress, the willingness to question, to challenge, and to seek truth beyond personal belief. Their discussions were not about winning, but about understanding. They knew that in the pursuit of knowledge, even conflict could be creative. Bohr's calm and reflective nature contrasted with Einstein's passionate certainty. Where Einstein sought clarity and precision, Bohr found beauty in ambiguity. He often said that the opposite of a profound truth may be another profound truth, a statement that captured the essence of quantum theory's dual nature. For Bohr, embracing paradox was not weakness, it was wisdom. The universe, he believed, could not be fully contained within the limits of human language or logic. Their debates shaped not only the direction of physics, but also the philosophy of science itself. They forced physicists to think deeply about what it means to observe, to measure, and to know. Bohr's insistence that reality depends on the act of observation led to the Copenhagen interpretation, the most widely accepted framework for understanding quantum mechanics. Einstein's criticisms, on the other hand, inspired generations of scientists to search for deeper unifying theories, including quantum field theory and the quest for quantum gravity. In the end, both men were right in their own way. Bohr revealed that uncertainty is woven into the fabric of nature, while Einstein reminded the world that the search for order and meaning never ends. Their dialogue transcended science, touching on the very relationship between humanity and the cosmos. Through their debates, the world learned that truth in science is not found in certainty, but in the ongoing conversation between ideas. As time passed, their friendship endured. Even in disagreement there was admiration. When Einstein passed away in 1955, Bohr mourned not the loss of an opponent, but of a companion in the great journey of discovery. Their exchanges remain immortal, echoing through every laboratory and classroom where physicists wrestle with the mysteries of the quantum world. Together, Bohr and Einstein shaped not only the science of the atom, but also the soul of modern thought, proving that the pursuit of truth is as much about questioning as it is about knowing. In the early decades of the 20th century, as the quantum world began to unfold, Niels Bohr stood as one of its most profound interpreters. His name became inseparably linked to the Copenhagen interpretation of quantum mechanics, a framework that reshaped not only the way scientists understood atomic behavior, but also how humanity thought about knowledge, observation, and reality itself. Bohr's interpretation was not a single formula or equation, it was a way of seeing the universe. It suggested that what we observe in the quantum world depends on how we choose to observe it, and that there is no single, objective picture of reality existing independently of measurement. This idea was revolutionary, not just for physics but for philosophy. Bohr's thinking began from the realization that classical physics could no longer explain the behavior of particles at the atomic scale. In the macroscopic world, things appeared stable, continuous, and predictable, but inside the atom, everything seemed uncertain, shifting, and dual in nature. Light could act like a wave in one experiment and a particle in another. Electrons seemed to occupy many positions until they were measured. To Bohr, These contradictions were not failures of understanding, they were clues. They hinted that the very act of measurement played a role in shaping what could be known. This became the essence of the Copenhagen interpretation, that the observer and the observed were inseparable. Bohr's guiding principle in this vision was what he called complementarity. He proposed that phenomena could be described in mutually exclusive but equally valid ways. For example, light could be understood as both a wave and a particle, but never both at once. Each description was true only within the context of the experiment being performed. The lesson Bohr drew from this was profound. To grasp the nature of reality, one must accept that no single viewpoint can capture it completely. Reality, in Bohr's view, was not an objective landscape waiting to be photographed, it was a dynamic relationship between nature and human inquiry. This philosophy unsettled many of Bohr's contemporaries. Einstein, as always, was skeptical, arguing that Bohr's interpretation left too much to chance. But Bohr responded with calm wisdom. He believed that uncertainty was not chaos, it was the natural limit of human knowledge. The uncertainty principle, developed by his student Werner Heisenberg under Bohr's guidance, captured this beautifully. The more precisely one knows a particle's position, the less precisely one can know its momentum, and vice versa. For Bohr, this was not a limitation of science, but a revelation about the nature of existence. The universe was not built to fit human expectations of clarity, rather, it invited humility in the face of its mysteries. In Copenhagen, Bohr cultivated an atmosphere where young physicists could wrestle with these deep ideas freely. His institute became a kind of temple for the new quantum philosophy. Conversations often stretched late into the night, with blackboards filled and erased countless times as Bohr and his students debated the meaning of equations and experiments. To Bohr, physics was not merely a technical pursuit, it was a quest to understand the boundary between knowledge and reality. He urged his students to think beyond numbers, to consider what those numbers meant about the way the universe revealed itself to human beings. The Copenhagen interpretation also had a moral and philosophical dimension. Bohr often reflected that the way scientists approached nature mirrored the way humans approached truth itself. To observe something was to participate in its revelation, not to stand apart from it. He saw science as a dialogue rather than domination, a collaboration between mind and matter. This humility toward nature, this acknowledgement that we can never step completely outside the system we study, gave Bohr's philosophy a timeless resonance. It was not just a theory of atoms, but a meditation on the limits of human perception. As experiments began to confirm the predictions of quantum mechanics, Bohr's interpretation gained wide acceptance. It became the foundation upon which much of modern physics was built. Yet even as it succeeded, it remained controversial. Some physicists longed for a return to determinism, a belief that the universe must be knowable in full, if only we could see deeply enough. But Bohr's interpretation reminded them that the quantum world was not like the world of human scale. It was stranger, subtler, and more beautiful. In its uncertainty lay its truth. Bohr's way of thinking influenced not only physics, but also other fields, philosophy, psychology, and even art. His idea that observation shapes reality resonated with the shifting perspectives of modern thought. Painters like Picasso and writers like Joyce were exploring similar ideas, that reality is not fixed but constructed, that multiple truths can coexist. Bohr's science and the art of his time shared a common spirit, the breaking of boundaries between observer and observed, between certainty and ambiguity. In the years that followed, Bohr often reflected on the philosophical depth of quantum mechanics. He wrote and spoke about how the discoveries of modern physics demanded a new kind of language, one capable of describing phenomena that defied ordinary experience. He insisted that physicists must learn to think in terms of possibilities, not certainties. The quantum world, he said, does not tell us what is, but only what may be. This perspective required not just scientific rigor, but intellectual courage, the courage to live with mystery. In the end, Bohr's Copenhagen interpretation became more than a scientific explanation, it became a symbol of a new worldview. It taught that knowledge is relational, that truth can be plural, and that the universe is not a clockwork machine but a living process of interaction. Bohr had transformed the atom from a solid, mechanical object into a shimmering field of probabilities. Through his insight, humanity learned that to understand nature, we must also understand our role within it. Niels Bohr once said, "It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature." In that simple sentence lies the essence of his interpretation. A recognition that science is not the conquest of mystery, but its respectful exploration. His Copenhagen interpretation remains one of the most profound ideas in human thought, reminding us that knowledge is not about certainty, but about deepening our relationship with the unknown. When the world entered the dark years of the Second World War, Niels Bohr found himself at the crossroads of science and morality. His lifelong pursuit of understanding the atom had unveiled not only the mysteries of nature, but also the immense power hidden within it. The same theories that explained the delicate structure of atomic energy levels now held the potential to unleash destruction on a scale humanity had never known. Bohr, who had spent his life seeking truth and harmony in science, was suddenly faced with the grim reality that knowledge could be both a blessing and a curse. His contributions to nuclear physics and his role during the Manhattan Project would forever link his name to one of the most powerful and troubling chapters in human history. In the 1930s, the discovery of nuclear fission changed everything. When scientists realized that splitting an atomic nucleus released enormous energy, it became clear that Einstein's famous equation, E=mc dials, had practical meaning. The transformation of a tiny amount of matter into vast energy was no longer theoretical. It was achievable. Bohr immediately recognized the profound implications of this discovery. Along with his collaborator John Wheeler, he developed the liquid drop model of the nucleus, comparing it to a drop of water that could elongate and split under certain conditions, releasing energy in the process. This model explained the mechanism of fission and made it possible to predict how uranium or plutonium could sustain a chain reaction. As the shadow of war spread across Europe, science was no longer confined to the pursuit of knowledge. It became a weapon. Bohr, a Dane of Jewish descent, found himself in grave danger when Nazi Germany occupied Denmark in 1940. Though he tried to continue his research, the situation grew perilous. In 1943, he was forced to flee his homeland in a dramatic escape that read like a scene from a film. With the help of the Danish resistance and British intelligence, Bohr was smuggled out of Denmark by boat to Sweden and then flown to England in a military aircraft. At one point, his plane flew so high to avoid detection that he lost consciousness due to lack of oxygen. When he finally arrived in London, he was welcomed not only as a refugee, but as one of the most valuable scientific minds of his generation. Soon after, Bohr was invited to the United States to join the top, secret Manhattan Project, the American effort to build an atomic bomb. It was a difficult decision for a man who had always believed in the peaceful use of science. Yet Bohr understood the stakes of the war. Nazi Germany was reportedly working on a similar weapon, and if they succeeded first, the consequences would be catastrophic. Bohr agreed to help, but his focus remained philosophical. While others calculated yields and designs, Bohr warned of the moral implications. He believed that the discovery of nuclear energy demanded international cooperation and transparency, not secrecy. He argued that the post-war world would need new global structures to control and share atomic knowledge responsibly. In Los Alamos, where the bomb was being developed, Bohr became a quiet yet profound influence. His deep insight into atomic structure helped guide theoretical understanding, and his discussions with scientists like Oppenheimer and Fermi inspired many to think beyond the technical aspects of their work. Bohr's calm demeanor and gentle wisdom earned him the affectionate nickname, "the father of us all." He often reminded his colleagues that science was not only about power, but about understanding. When the first nuclear test succeeded in 1945, marking the dawn of the atomic age, Bohr felt no triumph. He felt sorrow. The explosion in the New Mexico desert was both a scientific achievement and a moral tragedy. The world had crossed a line from which it could never return. After the war, Bohr became one of the strongest advocates for the peaceful use of nuclear energy. He met with political leaders, including Winston Churchill and President Franklin Roosevelt, trying to convince them to establish international control of atomic weapons. He feared that secrecy and competition would lead to an arms race, a prophecy that sadly came true. Churchill dismissed him as naïve, but Bohr's vision was far ahead of his time. He envisioned a world where scientific discoveries would be shared openly among nations, fostering trust and collaboration instead of fear and destruction. His efforts later inspired the formation of the United Nations Atomic Energy Commission and contributed to the early discussions that eventually led to the Nuclear Non-Proliferation Treaty. Back in Copenhagen, Bohr resumed his work at the Institute of Theoretical Physics, which had survived the war. He continued to explore the mysteries of the atom, but his focus shifted increasingly toward the ethical responsibilities of science. He believed that the atomic age demanded a new kind of human awareness, one that balanced knowledge with wisdom. To Bohr, the atom was not just a symbol of power, it was a reminder of unity. The forces that held the nucleus together mirrored the interconnections between human beings. Just as the stability of matter depended on balance, so too did the survival of civilization. Throughout the post-war years, Bohr became an international voice for reason. He received countless honors and awards, including the Nobel Prize, yet he remained humble and reflective. His speeches often returned to the same theme: openness. He believed that only through open communication and shared understanding could the world prevent future catastrophes. When asked how humanity should face the atomic age, he simply said, "Every valuable human being must be a radical and a rebel, for what he must aim at is to make things better than they are." In his later years, Bohr's Institute once again became a gathering place for scientists from around the world, including many who had worked on the bomb. There, discussions of physics intertwined with discussions of peace. Bohr's influence was so profound that even decades later, his students and admirers carried his vision forward, shaping both science and international policy. Niels Bohr's contribution to nuclear physics was monumental, but his greatest legacy was not an equation or a model. It was his moral courage. He stood at the intersection of discovery and danger, and he chose to use his voice for peace. His story reminds humanity that knowledge without wisdom can destroy, but knowledge guided by conscience can heal. The atom, once feared as a symbol of annihilation, also became a source of energy, medicine, and understanding, fulfilling Bohr's belief that every discovery carries both peril and promise. Through his life and his words, Bohr showed that science, at its best, is not about mastering the universe, but about learning how to live wisely within it. As the final chapters of Niels Bohr's life unfolded, his legacy began to transcend the boundaries of science itself. He was no longer just the man who had redefined the atom or the pioneer of quantum theory. He became a symbol of the unity between knowledge, morality, and humanity. In the years after the Second World War, Bohr continued to shape not only the course of physics, but also the ethical foundations of modern science. His ideas echoed across generations, influencing how we perceive both the visible and invisible worlds. Bohr's reflections on complementarity, his pursuit of international cooperation, and his deep belief in human understanding formed the core of his final mission: to remind the world that science must always serve humanity, not the other way around. In his later years, Bohr returned to Copenhagen and resumed his work at the Institute of Theoretical Physics, which had long been a beacon of innovation and collaboration. But his focus had evolved. He was no longer just trying to uncover the secrets of the atom. He was trying to understand the moral responsibilities that came with such knowledge. The atomic bomb had demonstrated the terrifying potential of human intellect when guided by fear or ambition. Bohr believed that the same intellect could also guide humanity toward peace and unity if it was coupled with honesty and openness. To him, the scientific spirit meant more than formulas and experiments. It meant a deep respect for truth and for the interconnectedness of all things. Bohr's principle of complementarity, which once explained the dual nature of light and matter, began to take on a new philosophical meaning. He believed that this concept applied not only to physics but to life itself. Just as an atom could be understood as both a wave and a particle, human existence could also hold seemingly opposite truths at once: reason and emotion, individuality and community, competition and cooperation. For Bohr, the ability to hold and understand these contradictions was essential for progress. The world, he thought, could only find harmony through acceptance of complexity, not through the illusion of simplicity. His speeches and writings often reflected this philosophy, blending scientific insight with a rare sense of wisdom and humility. Bohr also became a strong advocate for global unity in the scientific community. He believed that knowledge should not be confined within borders or political systems. In a world divided by Cold War tensions, he argued passionately for open communication between scientists from both East and West. He met with leaders, diplomats, and researchers, promoting the idea that mutual understanding through science could help bridge ideological divides. His efforts were instrumental in the creation of the European Organization for Nuclear Research, CERN, which became one of the greatest examples of international cooperation in scientific history. This achievement reflected Bohr's lifelong dream that science could unite nations through a shared quest for truth rather than divide them through fear and secrecy. Despite his fame, Bohr remained deeply humble and introspective. He lived simply, often walking or cycling through the streets of Copenhagen, always ready to stop and talk to students, neighbors, or fellow scientists. He continued to mentor young physicists, encouraging them to think not just about equations, but about the meaning behind them. To him, the pursuit of knowledge was a moral act, an expression of humanity's desire to understand its place in the universe. He often said that the opposite of a profound truth is not a falsehood, but another profound truth. This paradox captured his worldview, that wisdom is found not in certainty, but in the balance between opposing ideas. Bohr's influence extended far beyond the laboratory. His principles shaped the philosophy of science, inspiring thinkers, writers, and leaders around the world. He was honored with countless awards and became a respected voice in discussions on ethics, education, and global peace. Yet, he never sought power or fame. What mattered most to him was the continuation of dialogue, the endless exchange of ideas that fuels both science and civilization. His institute became a sanctuary for free thought, where young minds from all corners of the world could meet, question, and learn from one another. It was a living embodiment of his belief in open exchange and mutual respect. In the final years of his life, Bohr continued to write and speak about the responsibility of science in the modern age. He warned that the same intelligence that had split the atom could one day destroy humanity, if not guided by conscience. But he also believed in hope. To him, every discovery, no matter how dangerous, carried within it the possibility for good. It was up to humanity to choose wisely. Bohr's vision was neither pessimistic nor naive, it was deeply human. He trusted that the same curiosity that drove people to explore the mysteries of the atom could also inspire them to build a more peaceful and understanding world. When Bohr passed away in 1962, he left behind more than theories and formulas. He left a philosophy that continues to resonate through time. His face now appears on Denmark's currency, but his true legacy lies in the minds he inspired and the ideals he championed. The world he helped create is still shaped by his insights, from quantum mechanics to the principles of international cooperation. In every laboratory where scientists from different nations work side by side, in every discussion about ethics in technology, Bohr's spirit endures. His life was a testament to the belief that the pursuit of truth, guided by wisdom and compassion, can lead humanity not to destruction but to enlightenment. Niels Bohr's story is more than a chapter in the history of science. It is a mirror held up to humanity's conscience. He showed that the smallest particle could reveal the greatest truths about existence, and that real progress lies not in conquering nature, but in understanding our connection to it. His legacy reminds us that the power of the atom, like the power of knowledge itself, must always be matched by the strength of our humanity. Through his work, his words, and his unwavering integrity, Bohr changed not only what we know about atoms, but how we think about ourselves. And in doing so, he changed the world forever.